Okay. Hello. Hello, students. In the previous session, we have discussed about the heat and work and also first law of thermodynamics. Okay. And yesterday, some student has asked one thing. That's why work done is zero in case of free expansion as well as in throttling. Why you have taken that work done is zero. So now I want to elaborate this thing here. Why I have taken there zero. Okay. So first I to understand what is free expansion. Okay. Just wait. Suppose this is our room. Okay. And suppose this is our partition. Okay. This is our partition. You can say this is vacuum, and here gas is filled. Okay, here gas is what filled, and assume it is whole room is what insulated. Assume whole room is what insulated. Okay. Okay. So in case of free expansion, what's happened, my dear friends, you have to, what you have to in case of free expansion, you have to remove this one partition. Okay, when you remove this one partition, remove this partition. Okay, if you remove this partition, then what is going to happen, this gas that was inside this one, it going to fill the inside entire room. It's going to fill the what entire room. Okay. So now my question is that, is there any work done which happened or no? So here now question is that, sir, why there is no work done? So try to understand this one, my dear friends. Just I want to ask one thing. Suppose this is any surface, okay, in which this block is there, okay, and you are going to apply the force F, okay, and assume by the application force, this body are displaced at this distance, or we can say this distance is what x, let's assume, by the application of this force. So what will be work done, my dear friends? You can say, sir, F into x. Okay, F into x will be what work done. F into x will be what work done. Now my tell me one thing, my dear friends. Suppose if there will be no friction, why you are telling work done is F into x? You have to apply the some forces. After that, this will be what displaced, and this value of this force must be more than that of limiting friction force. Okay, if you apply the force, it is not move. If gradually you apply the force and one times reach, when the force applied by you is slightly higher than that of static friction, then your body is start to move. Okay, and in this case you are getting the work is what F into x. Now my dear friends, tell me, suppose if there is no friction, if there will be no friction, then what's happened? If you apply the slightly, or you can say very small force, still body can move, here friction is opposing the motion, so you have to work against the friction here. If there will be no friction, if you apply the slight force, very small force, still body can move. Are you getting point? And in this case you can say, since the value of force is 0.0000001 newton, you can say na 0.001. So what will be work done? What will be work done in this case? 0.000, are you getting na x? So it is approximate zero na. Work done is what approximate zero. So you can say you have to work against the what, against the resistance. Here resistance is what friction. Same thing. So whenever you have to work, you will work against the friction. Okay. But my dear friends, tell me one thing. Since there is a vacuum, and when you remove this partition, there is no resistance to the flow of the particle of this particular gas. So there is no resistance. They can move freely. Therefore, in this case, there will be not a work done. Hope this thing is clear. So in this case, there will be not a work done. Why? Because there is no any friction. If friction will be there, sorry, there is no any resistance. If resistance will be there, then you have to work. If no resistance, you haven't need to work. That is the why, dear friends, in case of free expansion, root thing if you talk, there will be work done will be what? Zero. Hopefully this thing is what? Clear. Okay. Now slight concept is there, limitation of first law. Limitation of first law. Limitation of what? First law. So let's see what is the limitation of first law of thermodynamics. Okay. So according to first law of thermodynamics, it is known as it is known as conservation of energy law. That means energy will be conserved. And if for closed system you talk, so dq equal to what? du plus tw. What is this? This is nothing but this is nothing but this is what? Conservation of energy. Okay, what? Conservation of energy. Now my dear friends, tell me one thing, is it sufficient? Suppose if any process is happening and it's follow the first law of thermodynamics, actually is this process is going to happen or not? You can't say. Suppose any process which follow the first law, then can you say that this process actually can happen in real life? This process can happen? No, you can't say. A process which have to follow first and second law both, only in such case you can say that this process is going to existing in actual, in the real. Okay, so how you can say this one? So how you can say this one, my dear friends? How you can say? So try to understand this one. Suppose this is your room. Okay, this is your room in which cup of tea is there. This is your cup of tea. Okay, this is your cup of tea. And if the temperature of cup tea will be high, then what will happen? If the temperature of the tea is more, then what will happen? Heat will leaving the this cup of tea and go inside the room or inside the surrounding. Okay, go inside the room or inside the surrounding. So you can say in this case dq equal to what? du plus dw. So not a work done is going to take place. So whatever energy is going to supply, it will dq equal to dw here. dq equal to du. Why? Because there is no work done. dw is zero. No piston work is there because it is a constant volume process. Let's assume. Okay. So my dear friends, we can say yes. It is going to transfer from T to surrounding room. But now tell me one thing: is it possible you put a cup of tea which is in cold condition, we can say, which is at a lesser temperature, and by default it will take heat from the room and start getting boil? Is it possible? Are you getting my point? Suppose this is a cup of tea. I am keeping it in the room. Okay. Is it possible that it will take the heat from the room and start getting boiled? No, is it not possible? But according to first law, is it possible? Why? It is just a conservation of energy, na? It is just a conservation of energy. It can say yes, dq equal to what? Du. So once du is increased, another time what you do? Decrease the du. Plus same thing you will get the, but it is not possible in actual life. In actual life, it is not possible. It is not possible that a cup of tea keeping inside the room will take the heat and start boiling. Not possible. Okay. So my dear friends, and second example I want to tell you. Suppose inside your room there is a bulb. Okay, there is a what? Bulb, and it's going to lighted your room. Okay? And in this case, heat will generate I square RT. Heat will going to generate. Okay. Now tell me one thing. By if now this is your room. Okay, and in this room bulb is going to, due to the right current is passing, so bulb is burning here. So this amount you will get the heat is I square RT. Is it possible that by this heat you can again get the light? You can again burning the bulb. Suppose burning bulb is off, can you get go or can you convert in this? No, you can't convert. So my dear friends, the drawback with the first law of thermodynamics is that it does not give information about the what? Direction. It is just a conservation of energy. It does not give information about the direction. So I have to study the second law of thermodynamics. This is also known as what? Directional law, because they gives the information about the direction of heat transfer. Till first law of thermodynamics, you can't say what is the direction of heat transfer. But in second law of thermodynamics, you can say what is the direction of heat transfer. That means, from second law, we can say heat is going to transfer from higher temperature body to lower temperature body, or from higher temperature to what, lower temperature. Okay, so you can say this through the what, second law. That, so this limitation is overcome in the second law. Okay, if you talk about the second law, so some points that you can discuss here, you know, in so there will be what, heat engine. Heat engine, what is the function to be performed by the heat engine? Suppose this is your temperature T1, and this is your HE, heat engine, and this one assume T2. Okay, so assuming T1 is more than T2, so what will happen, it will take the Q amount of heat Q1 and you will get the equivalent amount of work W. So you can write, so a heat engine is a device, or it is an engine which is used to convert heat into work. By the help of heat engine, you can convert heat into work. Okay, so here if you talk about the efficiency of this heat engine, so directly we can say work upon what, Q supply, or what is Q supply, W upon Q1. If you elaborate, so you will get the efficiency of heat engine. This will be 1 minus T1, 1 minus T2 upon T1. Okay, so this thing we will get by elaborating this one. Okay, now I will discuss what, COP, COP of refrigerant. Okay, just assume so assume this one is T1, again this one is T2, this one is Q2, this one is what, Q1, and you are going to get COP. Okay, so according to second law, you can say energy can transfer from lower temperature to higher temperature only when, if you give the external force, if you apply the external work, only in such case you can supply the energy from lower to higher temperature also, but you have to give the what, external energy, external work you have to give. So COP, you can write, COP is always given by desired effect, desired effect upon work. So what is desired effect here? In case of refrigerator, your target to cool the space, to keep a space at a lower temperature compared to that of surrounding. Okay, so that is the purpose of refrigerator. So we can say what will be their purpose. So we can say their purpose is to cool. So this one is Q2. What is the energy is supply? So W work is going to supply is what, W. Okay, but if you talk about the heat pump, COP of heat pump, so we can say directly what is usually COP of heat pump. The purpose of the heat pump is to keep the palace or keep the room at a higher temperature compared to that of surrounding. Okay, that means the target of heat pump is to heat a palace, to heat a place, to heat the room in which you are there, to keep the temperature of the room more than that of our surrounding. So we can say what will be this one, Q1 upon W. Okay, so this thing you have to keep in mind. Suppose if you talk here in this case, in, so if you apply the energy balance, so here in this case we can apply in the energy balance. So what we will get, we will get W plus Q2 equal to what, Q1, and by making elaboration, you know what will be W, Q1 upon Q2. So you can say COP of refrigerator will be what, this according to this one, Q2 upon Q2 upon Q1 minus Q2. Now, if cycle is, if refrigerator reversible, if refrigerator is reversible, then what is the meaning of COP? If reversible, so you can write T2 upon T1 minus T2. One more thing, this equation only you can apply if the cycle is reversible. If cycle is not reversible, then this one you have to apply. This can be applied in any circumstances, but this can be applied only when, if the cycle is what, reversible. Okay, one more thing you have to keep in mind here, T1, T2 and T, whatever T1, T2, that must be in the Kelvin. If you not keep in the Kelvin, you will get the problem. Okay, so temperature here must be in Kelvin. Now question is that Sir, what is the physical significance of COP? What is the physical significance of COP? My dear friends, COP indicates the running cost. COP indicates the what? Running cost. Higher the COP, lesser the running cost. Or you can say COP is directly proportional to 1 upon running cost. 1 upon running cost. Okay, so this thing you have to keep in mind. COP indicates the running cost. Higher the COP, lesser the cost, running cost, or lesser the COP, higher the running cost. This thing you have to keep in mind. Okay, and one more thing you have to keep in mind here, that COP of heat pump will be equal to COP of refrigerator plus 1. One more thing that you have to keep in mind, that COP of refrigerator can be less than 1, can be more than 1. Okay, but COP of heat pump always will be more than 1. Why? Because you know no, COP of HP is equal to COP of refrigerator plus 1. So COP of refrigerator can be anything, can be fractional, that means can be less than 1. Okay, can be more than 1, but COP of heat pump necessarily it will be always more than 1. Okay, because 1 point something will be, so it will be always more than 1. Okay, so now this was the some concept that I have to follow here. Now take some question. Take this question. This question is that a reversible heat transfer demands: option A, the temperature difference causing heat, the temperature difference causing heat transfer tends to 0. Okay, option B is there, what? The system receiving heat must be at a constant temperature. Option C, the system transferring out heat must be at a constant temperature. Option D, both interacting system must be at a constant temperature. So what should be the answer of this one? Okay, so what should be answer? You know, irreversible heat transfer, since it is talking about the what? Reversible. So you know, in case of reversible, you can say delta S universe is equal to delta S of system plus delta S of what? Surrounding. Okay, so let's assume, you know, suppose this is our system, and obviously this is our what? Surrounding, and assume heat is going to the system. So you can say, and this one is what? Reversible is given, so you can write here dq upon what? T1 minus dq upon what? T2. Why? Because dq amount of heat is taken from the surrounding, so dq will be same, but temperature of the system is assumed T1 and temperature of the surrounding assuming T2, so temperature is different. Okay, but you know my dear friends, for a reversible cycle, or for a reversible, the delta S universe is always 0. Are you getting the point? For reversible cycle, we can say delta S of universe will be what? Delta S of universe will be what? 0. So this quantity is to be 0. So this quantity is to be 0. Okay, now my dear friends, tell me, dq upon T1 minus dq upon T2 will be 0 only when if T1 equal to T2. If what? T1 equal to T2, otherwise it can't be 0. If T1 and T2 will be different, so it can't be 0. So according to the option, the temperature difference causing the heat transfer tends to 0. That means I am not telling it is exactly equal, slightly can be changed here, no issue at all, but my dear friends, slightly difference will be there, and negligible difference, approximate you can say same. So option A is the what? Correct answer here. So you can say A is what? Correct answer. Okay, now you can take this question. Figure below shows a reversible heat engine ER having heat interaction with the three constant temperature system. Calculate the thermal efficiency of the heat engine. Temperature T1 is given 1000 Kelvin, Q1 is given 100 kilojoule. Temperature T2 is given 500 Kelvin and Q2 is given 50 kilojoule. and temperature T3 is given 300 Kelvin, and Q3 is here. So what we have to calculate? We have to calculate thermal efficiency, okay? And you know, my dear friends, how we can get the thermal efficiency of this heat engine. So you know, this is given by always upon work upon heat supplied. What? Heat supplied, or you can say W upon QS. Are you getting my point? Now my question is that in this question, first of all, you have to calculate W, and after that you can find QS, and then you will get the efficiency, okay? So so then you have to think how you can calculate W, how you can calculate, okay? So see what is the key point in this figure below shows the reversible heat engine, okay? Shows what? Reversible heat engine. So this is the key point in this question, reversible heat engine. So you know, Clausius inequality, according to Clausius inequality, we can say for a cycle dq upon t will be what? Zero. Are you getting this point? So see, dq upon t will be zero. So what is the W? W is 60 kilojoule upon what is the temperature? 1000. So this is going to add, therefore I am writing here because this is going to add in the what? Heat engine. Again, what is Q2? 50. What is their temperature? 500. Now in this question it is very clearly mentioned here, Q3 is what? Q3 is what? Going out from this heat engine. So write down minus, okay? And Q3 upon what is the temperature? 500 Kelvin, okay? By solving this, I think you will get the value of Q3, and the value of Q3 will be 60 kg, 60 kilojoule, not a kg, okay? 60 kilojoule. So you have get the Q3. Now my dear friends, just what you have to do, you have to now by energy balance, by energy balance, what you will get by energy balance, you know, you can say Q1 plus Q2 into Q3 plus W. Why? Because by this you are getting here, you are getting some amount of work also W. So what is the value of Q1? You know, na, Q1 is what? 100. What is Q2? 50. What is Q3? 60 plus W. Now tell me, can you get the W? Yes, you can get. The value of W will be, I think, 90. The value will be what? 90. Okay, my dear friends? So now tell me one thing. What will be efficiency? What will be efficiency? 90 plus Q supply. Q supply is 100 plus 50. This one is supplied only. Okay. So you can write 100 plus 50. And if you solve, then I think you will get the answer. If you solve, then you will get the answer of how much percent? 0.6. That means 60%. So you will get 0.6, or we can say how much? 60%. Okay. So this thing you have to keep in mind. Clausius inequality is playing very important role in case of question, such kinds of question. If you solve, so you have to apply the concept of what? Clausius inequality. And for reversible heat engine, uh, del q upon t will be what? Zero. So by using this concept, you can use this one. Okay. Now take this question. Now take this question. Yes, Sutar, yeah, you are right. Okay. If a closed system is undergoing an irreversible process, the entropy of a system, option A, must increases, option B, always remains constant, option C, must decreases, option D, can increase, decrease, or remains constant. Okay. So this type of MSQ, or we can say objective question, we can expect, and this is, you know, conceptual question. So you find difficulty to solve such kinds of conceptual question. Okay, my dear friends. So what is in this question? Try to understand. In a closed system undergoing an irreversible process, which one process? Irreversible. So here irreversible is a key point. What? Irreversible is what? Here key point. Okay. The entropy of system, option A, must increases. Now my dear friends, tell me first thing, for irreversible process, you know, for irreversible process, if you talk about what will be ds for irreversible process, so if you have attended the session, that you will be well aware, it will be dq upon t plus something generation. What is this? This is called what? entropy generation. Entropy, what this is what entropy generation. And one important point that we have to keep in mind, I have discussed this thing in the class, that entropy generation can't be negative, even can't be negative. Entropy generation always will be greater than or equal to zero. This is very important point we have to keep in mind. Okay, so suppose if I am writing like that, dq upon t plus x. X is what entropy generation, because this thing is slightly difficult to write down, so I am use the this one x. So x is what, x is what entropy generation. Okay, x, you can say x equal to what generation. Okay, so I have used to write the x instead of this one generation. Okay, so what entropy generation, so entropy generation always greater than or equal to zero. Okay, if process is reversible, if process is reversible, in this case x will be zero. Process will be reversible, then x will be zero, that means entropy generation will be zero. Otherwise entropy generation always will be positive. This point you have to keep in mind. One more thing, entropy is a property. Entropy is what property, but entropy generation is not a property. This thing you have to keep in mind. Entropy is what property, but entropy generation is not a property. It depends upon the irreversibleness. What is the irreversibility of the process, of the path which is going to followed by this particular process. So entropy generation is not a property. Okay, now tell me one thing, my dear friends. If you now, if you talk about this one, about if you talk about this particular question, so what will be ds equal to dq upon t plus x. Okay, now since it is irreversible, so x will be always positive. Why? Because of irreversible, always more than you can say always positive will be there. Okay, always positive. So my dear friends, tell me one thing. If you apply, if you taking the heat from the system, if you taking the heat from the system, so this quantity will be negative. Okay, so this is negative and this is positive. X is what positive. So might be possible it can be zero. Might be possible if negative is more, so overall quantity will be negative. Are you getting point? Might be possible if entropy generation is more than that of dq upon t, so might be possible it can be positive. Are you getting my point? So you can say that it can increase, can decrease, or can remain. Are you getting the point? Get now. So suppose dq upon t. Okay, suppose this value this one is minus 6, let's assume, and entropy generation is plus 4. So what you can say, minus 2, that is entropy decreases. Okay, now assume dq upon t is just assume plus 5, and x is also, sorry, assume minus 5, assume minus 5, and this one is plus 5, then what is net? 0. Now assume dq upon t is 10 and x is 5, then what? It is positive. So you can say, my dear friends, in this case it can increase, can decrease, or can remain constant. Okay, so this point you have to keep in mind depending upon addition or subtraction of heat. Okay, now one thing, my dear friends, I want to tell you, just this is just you know, this is for irreversible process, if you know. So you can say dq upon t, okay, plus of x. X is what? Entropy generation. Now my dear friends, tell me one thing. If you talk about ds reversible, this is what? Ds reversible. So in case of reversible, you can write dq upon t. In case of reversible, you can write dq upon t. Now my dear friends, tell me, since now if I will tell that d in reversible adiabatic, in reversible adiabatic, if you talk reversible, that equation this one is applied. If you talk about adiabatic, so in case of adiabatic, dq will be what? 0. So we can say ds of irreversible adiabatic will be what? 0. Are you getting this point? So we can say reversible adiabatic is always isentropic. Are you getting that this point? That means delta s equal to what? 0. That means s1 equal to what? S2. That is what? Isentropic. So we can say reversible adiabatic is always isentropic. Always. Reversible adiabatic is always isentropic. But now, my dear friends, tell me one thing. Tell me one thing. In this case, we can say this is irreversible process. Suppose this is plus 5. Suppose dq upon t is minus 5 and entropy generation is plus 5. Still it will be 0. That means, if that means what? It is isentropic. So you can say all the isentropic process need not to be reversible adiabatic. Need not to be reversible adiabatic. This is important point. Even it is isentropic, means reversible. So general conclusion is that all the reversible adiabatic is isentropic, but all the isentropic needs not to be reversible adiabatic. So this assertion reason can be asked. Such kinds of question you can expect, okay, by MSQ. Such kinds of question can be framed. Hopefully this thing is clear. Okay, so now take some this question. Now take this question. What is this? One side of wall is maintained. One side of wall is maintained at 400 Kelvin and other at 300 Kelvin. The rate of heat transfer through the wall is 1000 watt and the surrounding temperature is 25 degrees Celsius. Assuming no generation of heat within the wall, the irreversibility in watt due to heat transfer through the wall is dot dot dot. That means NAT question. So how we can solve this question, my dear friends? Okay, one more thing, just I want to tell you in the previous discussion. Sometimes a student is going to confuse entropy change of ideal gas. Entropy change of ideal gas. Okay, entropy change of ideal gas. You know what will be this one? Delta S equal to Cv ln T2 upon T1 plus R ln V2 upon V1. Or similarly, another formula is that Cp ln T2 upon T1 minus R ln P2 upon P1. Okay. So what's happened in examination? Mostly I have seen a student is going to make a mistake here, that when I have to take positive plus R, when I have to take minus R. So my dear friends, I want to tell you one thing. By this, trick, you can remember this formula. Okay, I have seen from my experience that a student is going to stuck in this formula in the examination. So how you can remember this one? Try to understand. If in the question V1 V2 CV is given, then you have to apply this one. So try to understand. You can remember this one, that you have to add. How? Because CV is less. If CV is less, so making more, you have to add something. You have to add something. So you can write CV ln T2 upon T1 plus R ln V2 upon P1. Here CV, here you have to apply VT upon P1. Okay. Now, how another way? Suppose in question CP P2 P1 is given, then how we can apply? You can apply CP ln T2 upon T1. This one you have to remember. CP ln T2 upon T1. Since CP is more, so for making subtraction, making less value, you have to what? Decrease. So you can write minus R ln P2 upon P1. So in short, we can remember this one. Since CV is less, so you have to add R ln and CV, so V2 upon P1. Since Cp is more, so Cp ln T2 upon T1 minus R ln, and Cp is there, so P2 upon T1. So by this technique, you can remember this formula. And in exam, hopefully you can't going to confuse in this when I have to use plus ln, when I have to use minus R ln. So whenever Cp is there, you have to write minus. Why? Because Cp is more. Whenever Cv is there, so you have to write plus. Why? Because Cv is less. So by this way, you can use this formula, and you can expect at least one question from this, because this is very very important. Okay, one more formula is there, so that you have to remember also. Okay, now I take this question. Just wait. Okay, so what is this question? One side of wall is maintained. So let's assume I am making one wall. So suppose this is our wall. So one side of wall is maintained at 400 Kelvin and other at 300. So let's assume this one at 400 Kelvin and other as how much? 300 Kelvin. So in this question it is given that it is there is no heat generation. Okay, there is what? No heat generation is taking place. Since there is no heat generation, so you know what will be temperature profile. Temperature profile will be linear. Temperature profile will be what? Linear. Why? Because there is no heat generation. Okay. So the rate of heat transfer through a wall is 100 watt. The rate of heat transfer to the wall is 100 watt, and the surrounding temperature is how much? 25 degrees Celsius. That means let's assume this is our T infinity and this is how much? 25 degrees Celsius. Assuming no heat generation within the wall, the irreversibility in what? Due to irreversibility in what? Due to the heat transfer through the wall. No, tell me how the irreversibility you can find. How the irreversibility you can find. So irreversibility is denoted by I. So this is given by T node into, you can say, entropy generation. Okay, T node into what? Entropy generation. So first target in this question, T node, or we can say this one is T node or T infinity, whatever. We can say T infinity or T node, whatever. This is ambient temperature. So this one. So first target you have to calculate what? Entropy generation. Okay. So you know delta S. Can you write dq upon T plus of entropy generation? Okay. So in this question, another key point you can see here. Another key point that we can see here, what is this? Dq upon T. So this one we can write total will be what? 0. So what this one? Q1 upon T1 minus Q2 upon T2 plus of this generation, and by this you will get the entropy generation, or you can say value of X equal to entropy generation. You will get 0.833. Okay, so by this irreversibility will be what? T node into S, or you can say X, whatever. So what is the value of T node here? 298 multiplied by 0.833, and if you solve, then you will get this value is 248.23 watt. Okay, so this one, in this way we can calculate what? Irreversibility. Now take this question. This is a very important and good question. A steel billet of 2000 kg mass is to be cooled from 1250 Kelvin to 450 Kelvin. The heat released during this process is to be used as a source of energy. The ambient temperature is 303 Kelvin and a specific heat of steel is 0.5 kilojoule per kg Kelvin. The available energy of this billet is: option A is 490.44 megajoule, option B is 30.95 megajoule, option C is 10.35 megajoule, and option D is 0.1 megajoule. Okay, so how we can solve? A steel billet, that means a steel billet is there, the mass is 2000 kg. That means mass of a steel billet is how much? Mass of a steel billet is 2000 kg. Okay, cooled form temperature is how much? That means you can say delta T. What is delta T? Delta T is 1250 minus 450. Okay, so this one. Okay, so what will be heat released by the body? So you can say, right, mc delta T. Okay, so what is the value of m? This thing is 2000. Okay, what is the specific heat of steel is given 0.5 kilojoule. So you can write 0.5. What is delta T? So 1250 minus 50. By solving this, we will get the value of Q, and this value will come this one, kilo. Okay, so this is that value. Okay, now if you talk about the delta S, so if body is rigid, or any particular body, So their entropy is given by mc ln T2 upon T1. Entropy change is given by, suppose this is any body and I have to change the entropy change. So directly I can write mc ln T2 upon T1. Sorry, T2 upon what? T1. T2 upon what? T1. So directly you can find what is the value of mc. So 2000 multiplied by 0.5 ln 1250 upon what? 450. By solving this, we will get the value of delta as 1021.165. Okay. So now in this question, what is going to ask the available energy? Available energy of the billet is. So how we can calculate, my dear friends, available energy? How we can calculate available energy here? So this is important point. How we can calculate available energy? So this thing, so entropy change is how much? 1021.165. Okay, and available energy, that means A is always given by Q minus T node into delta S. Q minus T node into delta S. So what is the Q supply? This thing you have to keep in mind. What is the Q supply? So this one is, this value was, right, minus what is the T node? 3031021.165. Okay, and if you solve, then you will get this value 490.58 megajoule. 490 point how much? 58 megajoule. So available energy, you have supply how much amount? You have supply Q. Okay, in which this amount is going to waste. This can't convert it into work. Okay, so what is the available energy? So we can write this one and you will get the this one value. Okay, so in this way we can get what? Available energy. Okay, my dear friends, one important point that I have to discuss here. One important point that I have to discuss here. Second law of thermodynamics is also known as what? Qualitative law. So how we can say the second law is qualitative law? So experimentally I want to tell you. So my dear friends, suppose this is any our system. Suppose this is our source. This is any heat engine is there, and this is our sink, and this is what our heat engine. Sorry, this I will get work. This one is T1, coming Q1 and Q2, and this temperature is how much? Q2. Okay, so if I will ask the efficiency, so you can say efficiency equal to W upon Q, and if cycle is reversible, if cycle is what? Reversible, then you can say efficiency equal to 1 minus T2 upon T1. Okay, it's very now T1 is more than T2. Okay, T1 is what? More than T2. So my dear friends, tell me, I am telling you, assuming the process is reversible, I am assuming that process is reversible, I am assuming. Okay, so now tell me one thing. Suppose if I am putting T1 is equal to 1000, okay, and T2 equal to 300 Kelvin. So in this case, what will be efficiency? In this case, if you calculate, then we will get the efficiency is 0.7. That means W upon Q. Suppose now second case I am considering T1 equal to 800 Kelvin and T2 keeping the same 300. That means going to reject in the ambient. So what will be efficiency in this case? If you calculate, you will get 62.5. That means W upon Q. Third example I will take. T1 is equal to how much? 500 and T2 equal to 300. That rejecting at the same temperature. What will be efficiency in this case? We will get 0.4. That means W upon Q. What? W upon Q. Now, what you are going to analyze from this explanation, this thing, what you are going to analyze? In all the cases, I am going to transfer the Q1. In all the cases, I am going to transfer Q1. But what I am going to do here, actually, the temperature from which I am going to extract the heat, it decreases in all the cases. In this case, this one is 1000. In this case, 800 is there, and there is 500. But I am taking the same amount of heat. Q1 is same. Now, my dear friends, can you tell in this case work is maximum. In this case work is less than that of first case. Assume this one is first case, this one is second case, and this one is how much, third case. And if you talk about the third case, since q is same, so w is what, less. W is what, less or least. So my dear friends, here I can make one conclusion, that quality of work here, in case this one quality of work is good, but here in case of second, the quality of work is bad. But law of thermodynamics is always qualitative, because it gives information about the quality of work. Quality of work is good or quality of work is bad. But but first law of thermodynamics is also known as quantitative. Quantitative because it's just a conservation of energy, so quantity is major here, but here not a quantity, where quantity here quality is important. But in case of first law of thermodynamics, quantity is important, but second law of thermodynamics, quality is important. Are you getting this point? So what I have to do, in IC engine I will discuss, when I compress, then what's happened, temperature is increases. In IC engine, what's, when combustion is taking place, so before combustion what you do, before ignition you are going to compress. At the end of compression, ignition is going to take place. Why? Because as you compress, so temperature is increases. If temperature will increases, my dear friends, then burning is happening. So you are going to get the heat at a higher temperature. In this case, the work will be more. Therefore, in all the IC engine, what I have to do, I have to first compress, and after that, at the end of compression, temperature is increases, then burning is taking place, so that you can get the more work. Okay, so that you can get the more work, or more good quality of work you can get. Are you getting this point? Good quality of work you can get. Therefore, second law is known as what? Qualitative law also. Okay, my dear friends, now take this question. A heat reservoir at 900 Kelvin is brought into contact with the ambient at 300 Kelvin for a short time. During this period, 9,000 kilojoule of heat is lost by the heat reservoir. The loss in availability due to this process is, option A, B, C, D is given here. So how we can solve this question? A heat reservoir at 900 Kelvin is brought into contact with the ambient at 300 Kelvin. Okay, so just wait. So a heat reservoir, a heat reservoir at 900 Kelvin. So just assume this is our heat reservoir. Their temperature is given how much? T1 is given 900 Kelvin. Okay, brought into contact with the ambient at 300 Kelvin. That means this is our ambient, and temperature of ambient is given how much? 300 Kelvin. And heat here what? So you know, so this one is what? Q. For a short time period, during this period, 9,000 kilojoule of heat is lost by the heat reservoir. That means this one is 9,000 kilojoule of heat. Okay, the total loss in availability due to this process is, so now my dear friends, tell me, so you have to calculate the total loss in availability. Okay, so in this question, you know, T1, just assume T1 is what, or you can say T1 equal to T equal to 900 Kelvin, T naught equal to T infinity, that means ambient temperature, 300 Kelvin. Okay, and you know what will be change in entropy for universe? Change of entropy of universe will be what? Minus q q upon t1 or whatever plus q upon t naught. Why? Because from this it is going to rejected, therefore I'm writing minus sign. T1 or T or Q, it is going to add in the ambient, therefore I am writing the positive sign here because it is going to add to the ambient. Here you have taken from the, therefore what is the value of Q1? This one is 9000 kg. What is the value of T1? This one is 900, okay, plus this one is minus sign, okay. What is the value of Q? This one is 9000. What is the temperature? 300 Kelvin, okay. So by solving this, if you solve, then you will get, yes, minus 10 plus 30, that means 20 kilojoule per Kelvin you will get, okay. 20 kilojoule per Kelvin, okay. Now you have to calculate loss in availability. I haven't space, so just, so what will be loss in availability? That means I, this will be given by T node into delta S of delta S of universe. What is the value of T node or T ambient? So this is how much is given here, 300 multiplied by, what is this one? Universe is 20. By solving this, you will get the 6000 kilojoule, okay. 6000 kilojoule. So what should be the correct answer of this question? C will be the correct answer. 6000 kilojoule will be the correct answer of this particular question, okay. So my dear friends, this all about the second law, okay. In the coming class, in the next class, that YouTube free session, I will discuss the entropy, no, property of pure substance and thermodynamics relationship, and entropy also I will discuss there. So this thing, okay. So all these types of question we can expect, and also you have to increase, okay. So this all was, okay, thank you. Okay, one more thing I want to tell you on the behalf of GATEFORUM, my dear friends. You are providing the test series, so you can purchase the test series also. This will be much more effective to all of you. Test series you can purchase, okay. At the same time, you can join the for eGate live classes there, and from next batch you are going to launch the refresher course. In case of refresher course, all the video will be there, and live video session will be there, in which this session will be in the English and Hindi. That means bilingual will be there. Bilingual will be there. Okay, and yes, you can purchase all of this. And in case of refresher course, also we can access all the questions in the solve mode from the 2011 to 2020 gate questions. All the questions we can access in the video lectures that will be provided to all of you. And now this is the last time. So what you have to do, you have to make a proper strategy, and give more time to the study, because now approximate 2 month, not a 2 month actually, because mechanical 14th of February is there. So 1 month is you have, so you have to use your time in good way, okay. So thank you to watching this session. Thanks a lot.